All right. I will begin. Dear Father, we thank you for this day. I thank you for these students. Just ask you to bless our work today, Lord. In your name I pray. Amen. So I should start with something I forgot somehow in the, I don't know. Usually I talk about this earlier, but I should talk to you guys a little bit about center of mass. Okay, so what's the center of mass? So the idea is, if we got M1, M2, n masses, all right? Suppose you've got n masses. The question is, if we wanted to think of all those masses as a single mass at one point, where should we think about these masses collectively as residing, right? Now, if I gave you two equal masses, you could tell me what the center of mass was immediately, right? It would just be in between, yeah, half of the midpoint, right? But what if one of the masses was bigger and one of them was smaller? Then center of mass would be closer to the bigger one, right? So to be precise about all this, there's a simple definition. So what we need is the coordinates, well, the position vectors of each mass. So suppose this one is at R1. Suppose this one is at R2. Suppose the nth one is at Rn. All right? So, you know, physics is three-dimensional. These are three-dimensional vectors. If you have a two-dimensional problem, you can think of them as two-dimensional vectors. If you have a one-dimensional problem, you just need a number, right? Positive or negative, depending on whether you're left or right of the origin. And then you can talk about the total mass. What's the total mass? M1 plus M2, plus Mn, right? So you just add all of the masses together. That gives you the total mass. And the center of mass is equal to 1 over the total mass, and let's see here, times, well, M1 R1 plus M2 R2 plus Mn Rn. So this is center of mass. I'd say it's a weighted average, but that's not quite accurate. Would you like me to make it a weighted average? Here, I'll make it a weighted average. Check it out. Now it's a weighted average. See, because I'm just averaging the weights. I'm averaging according to the weight, like the more weight the mass has, the more it counts. And then you rescale by the total weight of all the masses collectively. But anyway, we don't want to multiply and divide by g like that, so let's just erase that and forget my joke. All right, center mass. All right, so let's look at an example. I'll give you a genuine three-dimensional example. Here we go. Suppose you've got one mass here, another mass over here, and a third mass up here, right? And you guys, you can tell me whatever you want. What do you want these masses to be? We can let them be different. Let's let M1 be 10 kilograms. M2 is 50 kilograms, okay. Is this a homework problem? No, you're just making those up? Maybe, all right. And so we should pick some coordinates to make this problem make sense. So let's say that the first one is at, I don't know, what do you think this looks, what does this look like to you? This looks to me like maybe 2 meters. And let's suppose that this distance over here is 3 meters. And I think that one looks like 2 meters as well. All right, so with this x, y, z coordinate system, we can write down the position vectors of these three masses, right? So I'll do that. So the position of mass 1 is apparently 2 meters. and then 0 in the y and 0 in the z. The position of mass 2 is 3 in the y, 0 in the x, and 0 in the z. The position of the third one is, let's see here, 0, 0, 2. All right? Now, suppose I tell you that there's a fourth mass, a mystery mass, which is added to this system. All right? And that mass has, I don't know, 100 kilograms. Such that the center of mass is at, let's say, 2 meters, 2 meters, and 6 meters. Actually, I'm not entirely sure that's possible.
6 meters?
I'm going to make that the center of mass is at the origin, just to make sure I'm not making a mathematically impossible question, which would be bad. Right? I mean, if you guys are physics majors, then I would give you problems that didn't make sense, and it would be your responsibility to explain to me as an instructor that, hey, that problem doesn't make sense. But you're 201 students, right? So I shouldn't give you problems that don't make sense, because that would be unfriendly. We wouldn't want that. You guys look happy today. You're all about to start dancing. Like you're dancing on the inside right now? I mean, I don't know. I can't tell. I don't see anybody. Physics makes you dance? I'll allow it. Okay, so, all right, moving along. So the question, did you understand the question? Now the question, I haven't stated it yet, but what's the question I should ask here? Where is the fourth mass, right? So that is an honest-to-goodness problem. Let's solve it. So we know that the center of mass is where? It's at the origin. And we know that it's equal to what? 1 over the total mass times m1r1 plus m2r2, m3r3, plus m4r4. We know everything there except for one thing, which is what? We don't know r4. r4 is what we're after. So we can solve for that. Should we do it? Let's do it. So what's the total mass? I've got 10 kilograms, insignificant, right? Plus 50 kilograms, plus 200 kilograms, plus the 100 kilograms. What's that give me? 360 kilograms is the total mass. And so we've got 0, 0, 0 is equal to 1 over 360 kilograms times what? Times 10 kilograms times what vector? 2 meters, 0, 0. M2 was 50 kilograms times the vector 0, 3, 0. And then I've got my, my 200 kilograms times the vector, the position of M3, which was 0, 0, 2. Right, close my, and then plus what? Plus 100 kilograms times the mystery position R4. So I suggest that the easiest way to do the math here is to multiply both sides by 360. What happens if you multiply both sides of this equation by 360? It goes away, right? So in other words, I could just do this, right? It doesn't change anything, does it? Now, my next suggestion would be that kilograms are annoying, and so divide by kilograms, right? So just cancel, cancel, cancel. It's everywhere. So now I just got, in terms of meters. What's this give us? If you add those together, what you got? You got 10 times 2 is 20 meters. What's this? We got 0, 150 meters, 0. What's this one? 0, 0, 400 meters. Plus 100 are 4. And so we can solve for it. What do we got? We've got 100 R4 is equal to, apparently, minus 20 meters, minus 150 meters, minus 400 meters if you put it all together. So if you add the 3 green vectors together, you get 20, 150, 400, but then we have to subtract it to the other side, which is why I get minuses. Now we're still not done. We have to do what now? Yeah, divide by 100, so we'll get R4. The location of the mystery mass is minus 20 over 100 meters, comma, minus 150 over 100 meters, comma, minus 400 over 100 meters. In other words, R4 is at minus 0.2 meters, minus 1.5 meters, and then minus 4 meters. And there you go. You've done a less complicated version of this in the lab this week in some sense, right? Like the lab, I call it the Star Wars lab. If you're in my lab this morning, you know why. It's because in this lab, we're trying to balance the force, right? So, I guess you're laughing on the inside. Definitely laughing with me, not at me. It's good, I think. Anyway, so there's the location of the mystery mass, and this is pretty much the most complicated center of mass question I can think to ask you. Right? Okay. So let us move on. Now, the more fun version of the center of mass discussion involves integration, continuous distributions of mass, and so forth. But we will not cover that because we do not have calculus. Yes. So, but this kind of center of mass gets you an awful long ways. So, just one other point of order here. Center of mass is interesting because, it also, if you have the masses connected in some sort of way, center of mass is going to be the balance point, right? So, but what we'd like to start talking about is things like this, like rotational things. So the question is, if I rotate this if I rotate this marker around like this, what's the kinetic energy of these markers rotating? Sadness. The rotational kinetic energy is 0 after that. Yeah, fair enough. You got me. All right, so next up, we are going to talk about rotational motion. Let's get into it. So here's the deal. We usually have in mind motion along some sort of circular arc. All right? And so along some sort of, I made it too big. I made it too big. It's too big. So along some sort of circle. Come on. I'm just not happy with it. Almost. Anyway, so that was supposed to be a circle. And if you're along a circle, right, and the circle has radius r, and you go, say, from this point over here to this point, so from P1 over to P2, suppose you move along this circular arc like this, what's the distance traveled? We call that distance arc length, right? We use the symbol s for arc length. So you could say s, this distance, and if this angle was theta, what's the relation between s and theta and r? Arc length s is equal to r times theta. That assumes, of course, that theta is in radians, right? So you guys know how to convert from radians to degrees? Maybe? Maybe not. Let's look at that just briefly here. If I want to take 30 degrees and convert to radians, what I do is I multiply 30 degrees by a conversion factor, which makes sense, which would be, let's say, pi radians. How many radians are there in pi? How many degrees in pi radians? There are 180 degrees in a pi radian. So the 30 and the 180 cancel to give me pi over 6 radians. So 30 degrees is equivalent to pi over 6 in radians. So another example would be 45 degrees is pi over 4 radians. 180 degrees is pi radians. If I've got 360 degrees, I have 2 pi radians. So this is another way of measuring angles, all right? And we use radians in this part of the course because otherwise, if we didn't use radians, the formulas I'm telling you would all get these really complicated conversion factors all over the place. So it's much simpler to simply work in radians. You must work in radians. All right, message received. Anyway, message given. Whether or not you receive it, that's up to you. So theta is the analog of position here. Next up, we talk about angular velocity. So omega is our typical symbol for that. That's equal to the change in theta over the change in time. Or if you like, theta 2 minus theta 1 over t2 minus t1. This is so-called angular velocity. All right? So that's angular velocity. You can also talk about angular acceleration. We use an alpha for that. Alpha is change in omega over change in t. So this is omega 2 minus omega 1 divided by t2 minus t1. Angular acceleration. So we can study the interrelation between theta and s. We can study the relation between omega and alpha and theta. In particular, if we have constant angular acceleration, the math works out pretty nice, and we have nice cut and dried formulas, many of which you should recognize. Let me write down some. So what I'm about to describe here is just a brief sketch of what you would call rotational kinematics. So the study of kinematics in rotational coordinate theta. And that is pretty simple, really. So if first of all, if alpha is equal to 0, then we have the following. We have that the change in theta is just equal to omega times the change in t. This is just like distance is equal to velocity times time. When is that true? That's true when the acceleration is 0, right? If the acceleration is 0, distance is velocity times time. If the acceleration is not 0, then things get more interesting. If alpha is not equal to 0, but alpha is constant, then we have the following relations. First of all, omega f is equal to omega naught plus alpha times time. So I'm basing the formulas off time 0, all right? And you also have the formula theta f is equal to theta naught plus omega naught t plus 1/2 alpha t squared. This is the relation between the final angle and the initial angle in the presence of a constant angular acceleration. So guys, if you understand the analogy here, can you tell me, if I start out this formula, I bet you can finish it. Omega f squared equals to omega naught squared plus what? I heard a 2 alpha times the change in theta. We have a winner, right? Because what she's using is the analogy. Well, maybe you're using it, I don't know. It could be high school physics, I don't know. But this, of course, is analogous to VF equals to V0 plus AT, right? This is analogous to our old formula XF equals to X naught plus V naught T plus 1/2 AT squared. This one, of course, is the analog of our timeless equation, VF squared equals V naught squared plus 2A delta X, right? And so there are also rotational analogs to the other kinematic equations, like the average velocity is equal to the average of the velocities. Remember that one? That's still true for angular velocity. I think I've written enough, though. I'm going to stop here for that. Let's look at an example, if you guys don't mind. Suppose that the angular acceleration is equal to 10 radians per second squared, and the wheel in question of radius, let's say, I don't know, 0.5 meters, is initially at rest. So find the following. The final angular velocity at t equals to 10 seconds. Find the change in theta over the first 10 seconds. And C, find the distance traveled. Well, that's not the. Meh. If something goes in a circle, what's the distance traveled? We said 2 pi r, right? What's the distance traveled in that motion? Is it 0 or is it 2 pi r? I believe the answer is 2 pi r, right? The distance traveled is 2 pi r. The displacement 0, that's true for the circle motion, but the distance, let's find the distance traveled by a point on the rim of the circle, rim of the wheel. All right? I think this example should pretty well illustrate these formulas I wrote down, all of which can be derived in exactly the same way I did not derive them for the linear case. Because I don't derive anything in here because, as I mentioned earlier, we don't have calculus. Yes. Now, my wife is teaching Physics 101 online, and she finds a way to explain things without math. But that's a dark art, which I'm not practiced in. So I'm not there yet. But my wife spends considerably more time teaching children than I do, so, you know, it's okay. All right, so A, you have to look at what we're given. We're given that alpha is 10 radians per second squared, right? We're also, if you tilt your head and squint, you can see that the initial angular velocity is given. What is it? It's 0, right? Because the wheel is initially at rest. So we're already in business to do part A. Omega f is equal to omega naught plus alpha t. But you put in the, we got 0 plus 10 radians per second squared times my time, which was given to be 10 seconds. What do we got? 100 radians per second. So that's the units, by the way, on angular velocity. It's radians per second. Does this make sense? I hope it makes sense. How about part B? Well, let's see here. We know that theta f is equal to theta naught, right? Or we could, let's rewrite it this way. Let's say that the change in theta, which is what we're interested in, is equal to omega naught times t plus 1/2 alpha t squared, right? But we know that the initial speed is, I said speed, but I meant angular velocity. The initial angular velocity is 0. So we have 1/2 times 10 radians per second squared times 10 seconds squared. What you got? We got 1,000 divided by 2, otherwise known as 500 radians. Wow, that's a lot. Now, if you object to 1980s lingo, you can always not abbreviate and just write out radians if you want. Let's see here. C. Yeah. Okay, so part C, we're supposed to find the distance traveled on a point of the wheel. So how do you do that? Round and round and round and round it goes. How many times? What's the arc? In other words, we're asking the question, what's the arc length traced out by that point? Right? So if you think about that, we're looking for s, which is equal to r times the change in theta. So we know r, which is what? 0.5 meters. And we know change in theta, which was 500 radians. And that gives us, 250 meters. By the way, the radians are not really a unit. They don't cancel out necessarily. They just kind of disappear. Yeah. Much like degrees. So another question I'll ask you while I'm doing something. How many revolutions? How many revolutions during this motion? Can you tell me? How would you figure out the number of revolutions? And also, while we're on the topic, what's the angular velocity, the final angular velocity in terms of revolutions per minute? Yeah, study group out there in the hall. Often thought we should put spikes along the edge of the hallway. So it's like when people sit down, they get like, oh. Or you could just every so often smear peanut butter. And we just have to do it a little bit, and then people would know you shouldn't sit there because you might get peanut butter on you. Or you could do paint. I mean, I'm open to other suggestions. Any number of things you could do. I'm also thinking of another thought I had earlier today was that we need to install some signs near the top of stairwells that say no texting. I mean, this seems like common sense, but it's a relatively common problem that people will be texting after they exit the stairway, and they forget that they're standing in a hallway where hundreds of people are trying to walk past. Right? Oh, they won't read the sign. It needs to be like an electronic warning, somehow to sense their phone is there and to text them. Stop texting. You need to move. Other people are around you, trying to go past this point. thinking about this. I don't know. I might have too much time on my hands. Let's see here. I'm sure I should have been saying something more useful at that time. I'm sorry. Oh yes, the number of revolutions. So the change in spooky. How appropriate, right? Yeah. Let's see here. Change in theta. You got 500 radians. This room is special. This is a special room. So if we want to convert radians to revolutions, very simple. What you do is multiply by 1 revolution over 2 pi radians, because that will give us the number of revolutions. Now, I can't do that one in my head. It's about 500 divided by 6.28. Somebody got a number for me?
I got like 79.6.
79.6? That sounds about right. So about 79.6 revolutions. So that's, if we wanted to put it in terms of revolutions. How about the angular velocity? If we want to put that, rewrite that in terms of, we want to convert to revolutions per minute. We got 100 radians per second, right? So to convert to revolutions per minute, you take that and you multiply by, first of all, a revolution divided by 2 pi radians, right? And then how do you convert seconds to minutes? You got yourself 60 seconds in every 1 minute, right? So we should multiply by 60 and divide by 2 pi to get the revolutions per minute, right? So what is the final angular velocity in terms of revolutions per minute? 79.6 revolutions per minute. Am I wrong? I could be wrong. I don't know. Of course, if I say RPM, that might be more familiar to you. That's what that means, revolutions per minute. Did I do that right? What's 600 divided by 6 pi? Isn't that... Oh, it shouldn't be 79.6. I don't know. I got... What is it? Is it driven me to look for my calculator? Oh, I have my calculator. Why am I not calculating? Let's see here. What's wrong with me?
I got like 955.
Yeah, I'm not sure I'm right there. You got 955? Yeah, that's what I got. So 954.9 RPM. There we go. Okay, so I should, I know you guys may or may not have a lot of experience with unit conversion, so I do try to do some of that on occasion in here, right? Let us move along. So that's rotational kinematics. Now what comes after kinematics is, what do we do after we studied acceleration and how it causes, how to understand motion with acceleration? Next thing we asked, the question was, where does that acceleration come from, right? And the answer to that was given to us in Newton's law, F equals ma, right? Force causes motion is our viewpoint. So in a likewise way, the question is, for angular acceleration, why is there angular acceleration? Where is that coming from, right? We like to say that angular acceleration comes from torque. So torque is a new idea. Let's see here. Let me actually go ahead and make a table for us. Just to summarize what's this, here's a... So on the one hand, I'm going to put old. Over here, I'll put new. The old x is the new theta. The old v is the new omega. The old a is the new alpha. Right? So we have position, velocity, acceleration. What's next? You might think about, mass. Well, mass, and I have avoided this up till now, but mass, the analog to mass is what's called I, which is the moment of inertia. Moment of inertia. And the moment of inertia is different for different objects. We'll talk more about this as we go on, okay? Like the moment of inertia for a sphere, the moment of inertia for a cylinder, the moment of inertia for a mass. These are moment of inertia for a rod. All different. Even for a rod, the moment of inertia for a rod is different if the rod is rotating, say, like the moment of inertia for a rod that's rotating like this is different than the moment of inertia for a rod that's rotating like this. So we have formulas for moment of inertia for a rotation around the end of the rod or around the middle. They're different. We have sphere, we have cylinder. I'll write them all down in time. They're in your textbook. But anyway, mass, the analog to mass is the moment of inertia. The analog of force is torque. Torque. There's more. What else have we talked about in the world of angular physics? Linear physics, right? Translational, if you will. Translational. Our new world, rotational. We also talked about momentum, right? Well, actually, before I do that, before I get to the basic players, how about a law? What was here? Net force equals to what? Yeah, ma, right? Over here, net torque is equal to I alpha. In the Star Wars lab, some of you have done, you are making the net torque be 0, which you achieve by balancing the forces, right? If the net torque is 0, the angular acceleration is 0, which is probably good, because if you had like a meter stick on a balance point and you hung some masses from it and it just started spinning, it would be disconcerting, right? So yeah, you're looking for an equilibrium, which is when the net torque is 0. What else is there? How about this? There's momentum, right? Linear momentum, P, which is equal to what? mv, right? What's the angular momentum? We use L for angular momentum. And angular momentum is I omega. Now, there's more I need to teach you than just this. We also have conservation of angular momentum when. So remember here, momentum conserved. When net force is 0, right? Over here, angular momentum conserved, Li equals to Lf, when net torque equals to 0. So if the net torque on a system is 0, angular momentum is conserved. This is the principle behind ice skaters. Like they conserve angular momentum, so like when they're twirling with their arms wide out, right? And then they bring them in, their rotational rate speeds up. In that process, there's essentially, in the moment, there's no friction, there's no torque on them over a brief period of time. And so since angular momentum is conserved over that brief period of time, the angular momentum they had with the mass spread out gets concentrated with the mass spread in. And we'll be able to understand that more mathematically here as we unravel these equations. But that's an example of momentum conservation. Is the ice skaters use that to their advantage to spin around in junk. Anything else we've talked about in translational physics you can think about that maybe we'd like to find energy. Energy, right? We had, what, kinetic energy? 1/2 mv squared, right? What do you think rotational kinetic energy is going to look like? If this analogy holds true, it should be 1/2 what? 1/2 I omega squared. In fact, that is in fact correct. Right. So there will be conservation of rotational kinetic energy as long as there's no, non-conservative forces involved to take that energy away. So what I'm starting to share with you is the fact that if we think about systems that don't just have translational motion, if they've also got rotational motion, there's more to the story than I've confessed to so far, right? There's not just the translational piece of the motion. There's also trying to find a marker, doesn't work. Unfortunately, this one kind of does work. So, there's energy when I throw this thing in two different ways, right? Yes, it's got the translational kinetic energy, but there's also rotational kinetic energy. If I could somehow throw it without it spinning, it would have less energy. There's energy in that rotational kinetic energy, specifically that much. All right? Now, torque is a little bit complicated. So probably we should start there. Let's talk about torque. So if we've got a pivot point, here, and this is the radius arm, which I'll use a vector for since it's a vector, all right? And then at this point here, we apply a force. So here's the point of application for the force. Then the question is what torque is produced by that force at that point. And well, by definition, the torque is equal to R cross F. Now, R cross F, let's see here. Maybe I'm going to write that force a different way just to make my picture better, like this. Sorry. Just draw another picture. You're fine. So this angle here we call theta. And so the magnitude of the torque is equal to RF sine of the angle between the radial direction, and the direction of the force. So before I explain what this R cross F means, because that's some new math that we haven't talked about yet. We talked about the dot product. Well, that's the cross product. All right, so I'm going to have to teach you guys that. Before I get into that mathematics, though, this torque, right? What would the value of the torque be for some different special cases of theta? Let's think about that before we think about anything else. If theta equals to 0, what's the torque? What's the sine of 0? Sine of 0 is 0, right? So if you think about theta being 0, that means that you're applying a force that is in the same direction as the line which connects you to the origin, and the pivot point, rather. So if you think about that, if you go to a door and you just pull on it, right, directly along the door, along the plane of the door, just pull straight out, it's not going to make the door, go any different which way, right? It's just going to sit there. There's no torque at all produced by just pulling on a door or pushing directly on it, right? To make the door swing, what do you have to do? You have to push perpendicular to the door, right? I mean, this is obvious, right? So the most direct kind of perpendicularity, if you will, is 90 degrees, or pi over 2 radians if you prefer. And 90 degrees gives me what sine of 90 degrees? Sine of 90 degrees is 1. So the magnitude of the torque is, at most, the product of the radius arm times the force, right? And its smallest could be 0. Let's talk about the cross product. So, some math. Cross product. So what is the cross product? Let me give you some big picture description of it. We take in you input, pair of vectors, let's say vector A and vector B, and you output a vector which we call A cross B, which is perpendicular to both A and B. So let's think about that for a minute. I've got a blue vector. I've got a black and red and pink vector. So here's my two vectors, right? I put them together. What direction is perpendicular to both of these? Looks like I need another vector. Come on. Ah! Come on. You can do it. You can do it. There we go. So my point, I would point out to you, to these two vectors, right? This is perpendicular to both of them, isn't it? But what else is? The other one, right? So this is what the cross product does, is it says, if one of these is A and one of these is B, I take my right hand, I point my right hand in the direction of A, right? I cross it into the direction of B, then my thumb points in the direction of the cross product. This is the right hand rule. So A crossed into B points up, the cross product's direction is up, right? On the other hand, if this is A and I cross it into B, I have to go down, right? So A crossed into B, I'm forced to put down. I can't, unless you're double jointed, I can't take my right hand and cross from A back into B like that, right? You have to cross like that, which forces you to go this way, and the cross product then of A and B would be down here. Now, so that's just how to visualize it with what's called the right hand rule, all right? There's actually a little formula, and the formula is relatively simple, and here's the formula. A cross B is equal to, and this is a popular mnemonic for it, determinant of, let's say, I hat, J hat, K hat. And what you do is you put the A vector in the second row rather, and you put the B vector in the third row, like that. And what that means, by definition, this gives us I hat, well, let me write out here. It gives us A2, B3 minus A3, B2, I hat, plus, parentheses, A3, B1 minus A1, B3, J hat, poor planning on my part, plus A1, B2 minus A2 B1 K hat. Now, I mean, that's an okay formula, but I think an equally good formula may be the best formula. I mean, how many of you are comfortable with determinants? So there is a certain pattern that you can see. So like to get this one, you look at this subdeterminant. So you got those, right? But I don't know, I think for you guys, since you have a formula sheet, maybe it's just wiser to just write down what I'm about to write down and take this as the definition. A2B3 minus A3B2, comma, A3B1 minus A1B3, comma, A1B2 minus A2B1. Like that. There you go. That is the cross product of two vectors, A and B. Let's do one with numbers in it, just to try to make it less scary, maybe. Oh, and let me make it physically relevant for you. So let's calculate the torque. So suppose we're applying a force of, let's say, 3 newtons, 2 newtons, minus 1 newton at the position, I don't know, 10 meters, 0 meters, and 7 meters. So suppose you're applying that force at that position. What's the torque about the origin? So to answer this, we just have to calculate the cross product. Calculate the cross product of the given radius arm R and force F. So let's see here. I'm looking at. I'm gonna bring the units outside since it doesn't give me joy to write newtons and meters 3 times. So let's just bring those numbers out. We can do that. Factor it out. We've got a Newton meter over here. Newton meter? Hey, we've seen that before. What's a Newton meter? Work, yeah, it's joule. So the units of torque actually are energy. It's kind of funny. All right, so what I'm doing now, guys, is I'm thinking of this as being my A. So this is A1, A2, A3. This is my B1, my B2, my B3, right? And I just have to plug it into the formula. So let's see here. I'm supposed to do A2, which is 2, times B3, which is 7. And I'm supposed to subtract from that A3, which is minus 1, times B2, which is, 0. I like 0. That's the first component. Now the second component is what? A3, which is minus 1, times B1, which is 10, minus A1, which was 3, times B3, which is 7, and then let's see here, what goes in the third component is 3 times 0 minus 2 times 10, I believe. All right. So let's clean that up a bit. What's our torque? What's the torque here? Don't forget your Newton meters. We got, looks like 14, comma, I think minus 31, comma, minus 20 Newton meters. So that's the torque here. What would the magnitude of the torque be? Square root, right, of 14 squared plus minus 31 squared plus minus 20 squared Newton meters, yeah? So like the magnitude of the torque, for what it's worth, which is not much, oh man. I hit the cube root when I wanted the square root, and I lost my number. So sad. I get 1557, then I got to square root that thing. I get 39.46. Newton meters. All right, so enough of that. Listen, if I did, there's some, cross product is a little bit scary in terms of math that you've seen in here, right? I mean, there's a lot of moving parts, isn't there? You got to keep track of these signs, you got to do it, be careful, right? It requires some attention to detail. We can check our work, though. There's something that should be true if we did it right. The dot product of the answer should be 0 with both of the inputs. So, moment of truth. If we take the dot product of the torque with 3, 2, minus 1, what does that give us? 3 times 14, 42. What's 2 times 31? 62. So 42 minus 62 is what? Minus 20. And then minus 1 times minus 20 is 20. So minus 20 plus 20? 0, right? Yay. The dot product of A, or R, the dot product of R with the torque is 0. That's comforting. That's probably enough evidence that it's right. But to be doubly sure, you could check the dot product of this with the other thing, right? So 10 times 14 is 140 plus 0 minus 140, 0. Bingo. So the torque is indeed perpendicular to both of the vectors. I don't know if you guys noticed this or not, but to check whether two vectors are perpendicular, it suffices to show that their dot product is 0. Because the dot product of two vectors is only 0 if the cosine of the angle between them is 90 degrees, is the cosine of 90 gives us 0. And that gives us perpendicular, right? So to check vectors being perpendicular, we look for dot product being 0. So if you can do this and check your work, you're already doing better than, I don't know, 30, 40% of the students I teach Calc 3 to, right? But this, you don't need calculus for this, right? You just need attention to a little bit of detail. It's not that hard, really. The question that most of you got right on the first test, more than any other question, was the dot product question. 21 of you got that exactly right. The rate of any physics word problem was not that high, right? Math is easy. Physics is hard. Am I right? Right. So, now, we end at 4, right? Oh, yeah, just checking that. Okay, so that is torque. Now, we should talk about, for a point particle, what's the moment of inertia, torque. I'll do more examples like that next time. I want to jump straight ahead to an interesting example with this stuff. I think we'll have time for it. Sorry, I forgot the attendance sheet today. My bad.